Swayam Prabha. Digital India. Educated India.
In the previous module, we have seen what is meant by an energy policy. We have also seen a framework to analyze energy policies, and we looked at the air quality in Delhi and the INDC India's commitment in Paris, and tried to analyze how we can analyze these policies and how they are being implemented. We are continuing with this, and we would like to take a look at some examples of energy policies. Let's look at access. And as you know, for every country, and especially for developing countries, the issue of access is one of the important energy goals. And that means we would like to provide affordable access to clean energy to the entire population. And in terms of this, in the Indian context, we want to have clean cooking fuels. Predominantly the largest chunk of our population still uses solid fuels, biomass, agricultural residues, typically in chulhas with very low efficiencies and with adverse environmental impacts in terms of local indoor air pollution, which causes an impact in terms of respiratory diseases. So the idea is, can we switch from these solid fuels to more convenient fuels like LPG, electricity? Can we convert them to modern biofuels? Can we look at solar cooking? And then the question of electrification. And we have had very significant progress in terms of connecting almost the entire country is now connected to electricity, but several households do not have connection because of a whole host of issues related to income, affordability. So rural electrification is another issue. So when you look at this, we can see that, you know, with increasing prosperity, the process of progress is where we started with initially just using human power, then going to animal power, and then going to renewable and natural power with wind and water, and then we created, basically everything started going into the fossil fuel, where you can transfer, and you had the centralized grid, and you had fuels, coal, oil, natural gas, and going towards electricity. So even when we think in terms of cooking also, there is this energy ladder where we go from solid fuels to gaseous fuels and electricity, and with income one actually moves towards using more convenient and cleaner fuels. What is the definition of energy access? Energy access is a household having reliable and affordable access to both clean cooking facilities and to electricity, which is enough to supply a basic bundle of energy services initially. And the idea is that this basic bundle, or the level, should keep increasing, and then an increasing level of electricity over time to reach the regional average. That means the idea is, this is the definition by IEA, part of the World Energy Outlook 2017 special report on access. The idea is that everyone should have access to clean cooking and electricity, and to meet their basic needs, and over time this should keep increasing to go towards the regional average, local or regional average. And if you look at this over the different income classes, when we look at, you know, the quintiles, quintile means divide 100 into 5 20 percentiles, that means lowest 20%, the next, and so on. So we can do that in terms of rural and urban. You can see basically the difference in terms of this where you will find that in the context of electricity, the lowest quantile has smaller percentage where they are using electricity. As the higher income, this goes to about 79%. In the urban, it's almost like 100%, and so on. So the fuel mix is very dependent on the income, and the lower income households are using biomass, traditional biomass, and maybe kerosene for the lighting. And so there have been a number of different policies and schemes. So in India, for households which are below the poverty line, an electricity connection is in many states provided free of cost, and this is being given for particular many cases. There is a Bhagya Jyoti and the Kutir Jyoti scheme, wiring, meter, one connection. There is a limit in terms of the connected load to be provided, but this is almost given sort of free of cost, and even the connection cost. So Bhagya Jyoti scheme, and now there is the Pradhan Mantri Har Ghar Sahaj Yojana. In many of these cases, there is an incentive for the initial upfront connection cost, and then there is a subsidized electricity use. However, still the uptake of some of these, there are issues related to that. We can look at now, if we look at the cooking, you can see this is from a paper by Ravindranath and Ramakrishna, where you see what happens, what is the implication of looking at different kinds of efficiency, low efficiency of the stove, and the emissions, the health hazard, respiratory diseases. It also results in global warming, and then there's also it can have more time taken for collection, and there's a stress on the biomass resource, there's a drudgery, and then also can result in poor soil quality. There are many different kinds of impacts. There are different kinds of chula designs, and it's possible. So this is a conventional kind of chula, if you see, using a solid fuel. There have been improved chula designs which can be smokeless, which can improve the efficiency, and some of these designs are also available in the public domain, where anyone can actually manufacture them. The initial capital cost is higher, but then there is an advantage in terms of the efficiency and the health impact. And of course, as we go up this stream, we are looking at kerosene and LPG with a much higher rate at which we are providing the energy or the power. The efficiencies are high, and there is much better controllability in terms of turning up and turn down. And this is a sort of pressurized kerosene stove, and this is an air fryer, an electric air fryer. So and many of these are, in terms of convenience, in terms of efficiency, in terms of emissions, they are much better. But some of these chulas which have been developed have been the estimate for this low smoke chula of the costs have been there, and you can see that we are talking in terms of a couple of thousand rupees, and one can think in terms of how to cost this. In general, the access of electricity is linked very clearly with poverty, and this is from the Global Energy Assessment. You can see many of the Latin American and African countries with high poverty levels also have less electricity access. We have been relatively low to pick up, but now we are going towards nearing at least 100% in terms of the village connections, and slowly going towards 70-80% in terms of households. The other issue which is there is that in many of these cases you will find that the quality of electricity in terms of number of hours of shortages and the reliability is another index that we can see. There are, apart from the centralized grid, there are options where we can have essentially different kinds of microgrids, and we can create a license or a licensee or a franchisee we can have a parallel license, we can have an off-grid collective, and there are different kinds of business models for this. We have had under these programs the rural village electrification program, village energy security program, the recently DDG, which was earlier the RGGVY, and we have essentially provided capital subsidy for many of these villages which are remote, and some of these actually provide almost 90% of the total project costs as a subsidy. The difficulty of course is that you have to have a mechanism so that subsequent maintenance, if you have a PV battery system, the battery payment and so on can be created. Again, there is even the National Solar Mission also, there is an off-grid component where we can look at this. You will be surprised to note that for low usage electricity, some of the remote rural areas for mobile charging, they pay a significant amount. It's a small amount of electricity that is required, but if you convert it into per kilowatt hour, you will find that people actually end up paying quite a significant amount, are willing to pay, but it's for a small amount of electricity. As we go up, go down, increase the number of energy services. The first important one is cell phone charging, then comes lighting, then comes entertainment in terms of TV and cable TV, and then comes the other things in terms of comfort, fans and refrigerators and so on. And so you can create this kind of a service and demand curve. There are different models, and we've had a large number of distributed generating models. Some of them are not for profit, some of them are for profits, and there are different kinds of prices and mechanisms, and if you are interested you can look at this in more detail. I am not going to cover this in this. And in many of these cases what happens is that there is local involvement in terms of operation and maintenance. For instance, in the Sundarbans there was the collective of the village energy and the village community, and they would actually train people. There was also load limiters, so that in case the load went beyond a certain point, and if that happened a number of times, the household would be cut off. There was a fixed rate. In some cases there are fixed rates, in some cases they are metered. There are also, we are thinking in terms of prepaid metering, and so there are a number of different kinds of things. And as you can see in terms of the measures which are there, many of these have been encouraging demand side management or energy efficient equipment, because if we use energy efficient equipment, then the requirement for the PV or the modules, the rating decreases, and this becomes overall much more cost effective. So just to give you some ideas, this is for affordable access. This is a small village in Maharashtra. There is a solar array, charge controller, battery and AC load, and if you look at it, you can see that most of the load is basically in the evening, and with the result that the capacity factor would be low, and this would result in high average prices. So it's quite common when you look at some of these. These are three biomass gasifier and PV. The energy costs are of the order of 30 to 40 rupees per kilowatt hour. Of course, we have worked out that if this is designed efficiently, they could be lower. They are often oversized, and that's because the demand estimation is not accurate. And then I talked to you about the Sundarbans model, where there is a cooperative for the renewable energy at different kinds of in the Sagar Island. There are 17 microgrids. There is a West Bengal renewable energy development agency. There's a power plant operator, there are customers, and then there's a committee of the beneficiaries, and this is how it sort of works. You can of course see when we look at costs of energy, if the load factors are low, the costs are going to be high, and so on. So whenever we talk about these microgrids or isolated grids, if they are linked with only a residential load, load factors are going to be low. The way to do this is to add some industry or add some base load or to add telecom towers, so that capacity factors increase and the average the costs of generation. We talked during the financing, I talked to you about the Selco example, where they have providing innovations in financing so that they can look at solar home systems. Another company which has been doing this is Desi Power, which has been aggregating different kinds of biomass based power solutions in Bihar and putting this in terms of the total amount of CO2 savings, and so getting the credit in terms of the certified emission reduction, and then getting it registered under the clean development mechanism. They are also tied up with the telecom towers. The problem in many of these cases is that when the grid has come to these locations, at some points they have not been able to compete. So they have also looked at fixed costs in terms of irrigation pumps and households. And Husk Power, similar, again biomass based power, but they initially started with their own prize money, and they looked at overhead pole wiring. They directly reached the end user. And if you see in terms of the usage of for cooking, you look at rural and urban households over time, and you can see that the mix of different kinds of fuels has changed over a period of time. You can look at this from the NSSO data, which is collected every few years, National Sample Survey, and we have you can see for the income deciles, this is plotted the energy consumption, the end use energy and the total energy. And the interesting thing that you will find is that the end use energy in the case of urban, the total energy actually initially declines and then increases. And this decline is because then with the in the lower income classes, you are using more traditional fuels, and because of that, though the end use energy is keeping on increasing, and because of the poor efficiencies, you can see this kind of a mix. This is from a paper in 2012. One can then make a comparison in terms of calculations. Now, it is possible to have modern biomass based energy systems which will give you actually biomass gasifier based systems which give you LPG quality fuel and LPG and control. So for instance, if you look at this flame, this is a rice, this is based on a gasifier, but it is firing rice husk, and you can see that this flame is just like the LPG flame. And so this is another thing which can be done. There are the stove designs, and this is done by the research group at IIT Bangalore. This is the Urja stove. It needs pellets like this. Now what happens here is that this becomes more efficient. It improves the reduces the emissions, better from a health impact, but then the feedstock, earlier biomass was just being collected and there was no price. Now this we have marketized and we are now creating this as a market where they will have to buy these pellets, and we need to have this chain. So there is a cost implication of this. This is an innovation from the US. It's a BioLite stove, and the interesting thing about this stove is there is a thermoelectric generator. We are using the exhaust of the of the stove, and this is used to generate electricity. It can run a small fan which will cause the induced draft, and it can also charge, it can be connected to get an LED light, or you can charge your cell phone. So this is an interesting kind of innovation. Of course, this will cost more than the normal stoves. There are different kinds of biomass based stoves made by some of the technical NGOs in Pune, and the compact biomass gasifier you can see. And So in all of these, we can think in terms of different kinds of subsidy mechanisms, but when we talk in terms of cooking, it's needed for us to estimate when we think in terms of the environmental impact and the health impact. And one parameter which is used for this is the disability adjusted life years. So one disability adjusted life year is thought of as one lost year of healthy life, and the sum of these disability adjusted life years across the population or the burden of disease can be thought of as a measurement of the gap between current health status and an ideal health situation where the entire population lives to an advanced age free of disease and disability. This source is from the World Health Organization. You can see that this disability adjusted life year is the year of lost life and the year and the lost days of work. So what happens is, because of disability, if people are not able to work at their full efficiency, and they have to take leave, so that's one. And then if people die at a year which is before their expected life tenure, and so these are computed again in terms of based on the emissions, the health impact, respiratory diseases, and the number of deaths, and then in that population statistically the age distribution who are impacted, then for each one the number of years lost, and then that's multiplied by the population. So this is something you can get more details both in the World Health Organization as well as several papers which exist. But this is one way to quantify, and in doing this we can see how indoor air pollution compares with, for instance, outdoor air pollution, or with actual diseases and their impacts, and you find that it is in most countries this is a very significant, it comes in amongst the top few in terms of the health impact. And this is something where we can see if we have a scheme where we can reduce the emissions, then we can adjust this and compare. So there is this whole chain, as we said, emissions, then the exposure, and this depends on a variety of things. That means what is the time activity profile, what is the ventilation of the stove and the home, and what kind of fuel is there, location of the kitchen, gender, age and cooking habits, demographic variables, and the cultural practices, ethnicity, income and education, fuel type and stove type, the energy market structures, temperature variables. So there are a whole host of different parameters, and many of these can be affected by policies. So now let's look at taking some of this that we the earlier things that we have done and make a simple calculation to see what it means when we think in terms of looking at a switch of fuels. So let's consider a poor rural household. It uses 3 kerosene lanterns with the following data. The cost of the lamp is 100 rupees, life is 5 years, annual O&M cost is given as rupees 20 per year, and the usage is 4 hours per day or 20 milliliters of kerosene per hour. Price of kerosene, market price, is given as 35 rupees per liter. We are given that the kerosene is 82% carbon by weight, specific gravity is 0.8. We want to replace it by a solar PV lantern. Capital cost is 550 rupees, life 10 years, 150 rupees, battery 2 years. Now the question that is asked is, considering a household that uses kerosene, calculate the annual cost and the CO2 emissions for each kerosene lantern and the viability of replacement with solar. Use a residential discount rate of 60%. So let's look at first household that uses kerosene. Let's calculate the annual cost. Annual cost will be first let's calculate annual kerosene used annual kerosene used is going to be, there are 3 this is sorry, let's see, for each of the, let's do this first for each one. Each of these kerosene lanterns is used for 4 hours, okay, and in each hour it is using 20 milliliters. So, 4 into 20 by 1000 into 365 days. If you calculate this, you will get this as 29.2 liters of kerosene. So, that means for the household, if we are using 3 lanterns, 3 into 29.2, so 87.6 liters. And if we look at the cost, this will be 87.6 into 35, comes out to be rupees 3066. We have also said that there is a operation maintenance cost of 20 rupees per lamp annually, 60. So, this comes to 3126 rupees, fairly high amount. If we look at an annual CO2 emissions, let us calculate annual CO2 emissions. This will be, now we are using 87.6 liters into density 0.8, that's about, that is, this turns out to be 70 kgs. In each kg has 0.82 kg of carbon per kg of kerosene into C plus O2 giving you CO2. So, 44 by 12, and this turns out to be 210 kg of CO2. Annual CO2 we have calculated. The next question was, so is it viable, annual cost and the CO2 emissions. So, annual cost is 3126 rupees and the CO2 emissions is 210 kgs. So, viability of replacement with solar. So, when we look at a replacement with solar, we are looking at a total cost is 700 rupees, right, and 700 rupees is saving us annually, we are saving around 3000 rupees. So, the payback period is less than a month, less than a year, and so from that point it may be viable. However, if we now look at it in terms of, it seems to be viable. Let us look at it in terms of the annualized life cycle cost. Annualized life cycle cost. If we look at the annualized life cycle cost of for one lamp, this is going to be 100 into capital recovery factor 0.6 and 5 plus 20 plus the 29.2 into 35, and if we look at this, you will find that you can calculate this as, this turns out to be 0.663 is 1108 rupees. What is the annualized life cycle cost for solar? This will be 550 into capital recovery factor 0.6, 10 years, plus 150 which is the battery, and we said battery life is just 2 years. So, 0.6 and 2, plus we can add in both the cases that that 20 rupees is going to be there. So, this is 550 into 0.6055 plus 150 into 0.985, and this turns out to be 632 rupees. You add 20 rupees to this, which is the O&M, so 652 rupees. So obviously the ALCC seems to be lower. Even if we forget about this cost, that means instead of 1,100, I mean 60, instead of 1,100 it's like 1,000 and 652. So from this point of view, at full cost of kerosene, this doesn't look to be viable. This looks to be viable, solar looks to be viable. If we suppose there is a subsidy on kerosene and this is 18 rupees per liter, then this will be 18 into 29.2. So now this is rupees 525.6. This now, when it's subsidized, it is lower than the solar. So it will not be viable to shift to solar once you have subsidized kerosene. So the question now is, calculate the cost of lighting for each solar lamp, and if the model was to have a lease model, calculate the effective monthly payment. So for each solar lamp, if we look at it in terms of the calculation that we had done, it was 652 divided by 12, which is 560 and 52, 448, something like 54 or 55 rupees per month. So that could be a way in which we could do this. This is of course with the high discount rate. If we calculated this with a societal discount rate of 10%, then this is going to be much lower, because we are going to do 550 CRF 0.110 plus 150 CRF 0.12, and with the result that this is just going to be, you can calculate this, you will find that this is 341 rupees, and this is now I think this is 0.167, and this is 1627. This is 0.576. So if 341 divided by 12, something like 25-26 rupees per month. And the advantage then is that this company, which has the government or a public sector company which has a lower discount rate, now needs to only recover at the rate of 25 rupees per month. And we can also look at, if you see the subsidy that we had, the subsidy per lamp was now 17 rupees into 29.2. So you will see that we can also provide that subsidy. If we want to keep that subsidy constant, we can even reduce the initial capital cost by that amount, and then we can have reduce the lease payments, so that instead in a month we are only paying a lower quantity. The advantage there now is that because of the higher discount rate, the household is not able to upfront pay that initial amount, and is now able to just pay these monthly payments. So now the question then is, the last part of the question is that, would you recommend complete removal of the kerosene subsidy? And when we think about this, the kerosene subsidy is also to provide for kerosene is often used for cooking, and in some of these cases, for instance, if there is no if there is a problem in terms of the battery and the solar, there will be an incentive for this. There will be, what will be the issues in implementation? There is a transaction cost of actually providing this. We need to provide support for maintenance. And what are the disadvantages of the solar lantern? We have to ensure that the PV modules are kept in the sun so that they get charged, and then the usage pattern and the discharge. So we would need to have a hybrid where we still can maintain a certain amount of kerosene and this. But this gives you an idea of how we can look at policies and we can look at economic impacts of putting the subsidies. The kerosene subsidy is incidentally being phased out, but in most cases where we can calculate, you can actually see that the solar subsidy, replacing the kerosene subsidy by a solar subsidy makes a lot of sense.